Today we are going to talk about control volume and Newton's second law. For control volume, we have several different control volume. The first one is fixed non-deforming control volume, and in general, in many fluid mechanics problem, we can use control volume analysis to solve the problem. And the good judgment is required in defining the control volume used in solving a problem. There are important consideration that what exactly to leave out of and what to leave in the control volume. There are the consideration that is important. So if and also in this fixed control volume, in many application of fluid mechanics that we are using control volume, an appropriate one is almost the fixed and non-deforming control volume. So let's show it through this example. So we have a joint, we have a pipe joint that water flow in the pipe steadily, and the information that we have is we have V1 right here. Let me change the color. So we have this this is as V1 here, and also we have, and the value is 0.5 meter per second, and also we have another flow that is exit the section 3, which is V3, and the value is 1.2 meter per second. And also we have a small hole here, and what we have is the volume flow rate of 0.01 meter cubic per second. And then the other thing that we also have the area of 1, which is right here, and then we have area of 2 here, and then we have area of 3, which is right here, right? So then to solve this problem, first let's show the normal vector on the surface. So this is the normal vector on the surface 1, which is perpendicular to that, and this is normal surface at section 2. This is at section 3, and this is at section 4, right? And also let's consider also the velocity here. Let's say the direction is coming down, and this is V2, but we are not sure about the direction, right? We just now use this direction. If the value that we got is positive, it means that this guess is right. If it's negative, meaning that the guess of the fluid coming out of section 2 is wrong and it's going in. So let me just write down, we assume that, right? So we assume this direction. Oops. Okay. So we assume this direction, and if I want to use the previous material, let me go there and bring the material that I taught in the previous video. So let's use this one. So we have this formula, and I mean the conservation of mass. Right, we have this one, and let's just put 0 here. And the assumptions that we have, I'm going to talk about the assumptions at the end of the this chapter as well, this video I mean. So the assumption that we have, so it's a steady flow, right? So let's say it's steady flow. So because it's a steady flow, this one right here, this term right here, because it's the derivative with respect to time, so this term here gonna be 0, right? And then another assumption that we can make, because we have water, we can say that this is incompressible flow, meaning that density is constant, right? And then the other assumption that we can make is that we can say that we have constant properties, and because we are assuming the velocity in one direction, so we can also say that we have one-dimensional flow, which means that, for example, we have uniform. So if I want to consider this formula right here, because the velocity is uniform, the rho is constant, and also we have constant properties, so we can get rid of the integral and just use rho VA, which is our m dot, right? We talk about it, how we can use that one, which is we kind of use all of this assumption that we have to get this formula, right? So now let's just apply this formula for all of these 4 sections that we have, right? Because we need to use this control. Let's say if this is my control volume right here, right, if this is the control volume right here, then we have 1, 2, 3, 4 section that we need to apply the information of these 4 section on our control volume. So let's get started. So we know that this the conservation of mass say that all of the mass in the system should be conserved. So if I have at the first section we have rho 1, and then we have v1 times a1, and because v1 is going to the system, right, to the control volume, remember we talked about v dot n, the the dot product. So because of that, I say that if it's going into the system, the sign of v going to be negative, right? And then at section 2 we have row 2, we have v2, and we have a2, right? And it's coming out of flow, so it should be positive. Now on section 3 we have row 3, v3, and a3. So here it should be positive again because it's coming out of flow, so it's flow out, right? And then we have at 4 we have row 4, v4, and a4. Again, this is a positive sign right here, and we know that v times a going to be flow rate, right? We're using the, for section 4 we need to use the flow rate because it just give us the question just give us the volume flow rate at 4, right? So this is why we just consider volume flow rate there. So if we put all of the value that we have, and we know that all of the densities are going to be the same, which is density of water, so we're gonna get, and we know v1, we know a1, we know a2, v3, a3, and we know q4. So it means that we can solve it for v2 right here, right? Because we don't know it. If we put all of the value there, we can get v2 is equal to minus 0.45 meter per second, and this is the velocity. And if you remember, I said that if we get the minus sign, it means that our assumption right here is wrong. The direction of velocity is wrong, and it means that the correct flow direction is into the control volume. So another control volume that we can use called moving control volume. Some problem are most easily solved by using this kind of control volume. In this control volume, we are using the definition of relative velocity. So we say that v is the absolute velocity, and then w is the relative velocity. So vcv is going to be the velocity of the moving control volume. And for a system and a moving non-deforming control volume, if we apply the Reynolds transfer theorem, it leads to this equation right here. And let's show it through this example. So we have a moving vein right here, and there is a nozzle that the flows of out of the nozzle going to the moving vein, right? So we have v1 right here, which is the velocity coming into the control volume, and the vein is moving with velocity of v0, right? And so if we consider VCV as V0, right? Let's write down all of the let's write down the relative velocity to the control volume for this system. So if we use this formula right here, we have V is equal to W plus VCV, right? And because the vane right here is moving with the velocity of V0, so it means that, and this is our control volume, the dashed line. So it means that our control volume is moving with the speed of V0, right? And then now we are trying to find W, so W gonna be V minus VCV, right? So if I want to write down the relative velocity at section 1, so W1 is going to be V minus VCV, and in section 1 V is V1 and VCV is the vane velocity, right? And also for section 2, again we are using this formula right here, and so V is V2, which is the absolute velocity, and then V0 and V2 is right here. I forgot to show you. So we have one fluid that is coming here, and if we just follow the fluid, it's coming out of the system right here. And then we also consider the W2 here, and let's consider W1 right here. So we have V2 minus the velocity of the vane, right? So yeah, we're gonna solve some question based on the moving control volume as well.